So let's start chapter number 2. This chapter is about analytic functions, the type of functions that we study in complex analysis. So this is where complex analysis really begins. Today, however, in this video, we are not going to see the definition of an analytic function. Instead, let's see complex valued functions themselves with some examples. Let's see what type of functions they are. Let S be a subset of the set of complex numbers. Non-empty subset, that's understood. A function f from S into the set of complex numbers is called a complex valued function of a complex variable. For this type of functions, the input is a complex number and the output is also in general a complex number. And we call the set S the domain of definition of the function f. Do not confuse this word domain here with what we defined in the previous video, in which we defined a domain to be an open connected set in C. Sometimes these sets will be domain in that sense, but that's not necessary. They are just sets from which inputs of a function come. Now we often write the function f like this using such an equation, which shows the name of the function, the independent variable and the dependent variable. So these are the complex values which are the outputs of the function. So that's why such a function is called complex valued. That is, they give complex values as outputs of a complex variable, this independent variable. In order to specify a function, you already know these things from calculus, still I am repeating. In order to specify such a function fully, only giving a formula like this is not enough. You also have to say what the domain is. But if the domain is not mentioned, which is frequently the case, you will just see a formula like this and it will be said that it's a function. In such cases, you have to assume that the domain is the largest set of inputs that is possible. We will see the examples there, these things will become clear. Now say we write these objects W and Z in their true form, that is, they are complex numbers, so let's write them as complex numbers. So W is U plus IV and Z is X plus IY. Then this equation looks like this. And now from this we are going to observe something. This is the observation. Note that both U and V are functions of X and Y. It just simply means that if X and Y are given, if some values of them are given, then you get a unique value of U and a unique value of V. In that sense, U and V are functions of X and Y. And to show their dependence on X and Y, we write like this. U equals U of X comma Y and V equals V of X comma Y. So you see that in order to study functions of this type, you automatically have to study functions of two real variables, which are real valued functions. These two are real valued functions, but they are functions of more than one variable. That automatically comes here. Now before we proceed further, let me draw your attention to something which we often overlook. It is this type of notation. Do we really understand what it means for U to be a function of X and Y? Just now I said that it just simply means that for given values of X and Y, there exists a unique value of U, for which this equation is true. But actually what that means is that in the background there is a function, in which if you put some values of X and Y, then that function gives U as the corresponding output. What is confusing about this equation is the use of the letter U on both sides of this equation, but with different meaning. On the left hand side, this U is a complex number or a complex variable, let's say, because it can change. On the right hand side, however, U is a function. Ideally, we should not write U here. We should give the function in the background some other name. say f, I mean we have used f here, say g something. But in order to not write, not use many letters, and in order to link this with the function, we choose to name the function also u. That sometimes creates confusion. But if you already know these things, so then there is no confusion. That is the real meaning. This is just the name given to that function in the background which has u as its output for given inputs x and y. Just like that, v is a function of x and y. Here also you can write, if you want you can write something else. Okay, that won't be a problem. So with these new notations, this equation looks like this. F of x plus iy in its place I have just written f of z, and on that side, which is now the right hand side, we have shown the dependence of u and v on x and y. So you have got u of x comma y plus I times v of x comma y. This is called the real part of f of z, and this is called the imaginary part of f of z. So the real part is itself a function, and so is the imaginary part, and both are real valued functions of two real variables x and y. Now you may choose to write the input z in polar coordinates instead of Cartesian coordinates. In Cartesian coordinates you write it as x plus iy. In polar coordinates you would write r times e to the power I theta. This however can be done only when z is non-zero. Okay, keep that in mind. But anyway, if you do this instead of writing z as x plus iy, then now your u and v become functions of the polar variables r and theta. Let's see next example 1, where we consider this function f of z, which is nothing but the reciprocal of the input. So this function is only given by this formula and the domain is not specified. In that case, by convention, you have to choose the largest possible set of complex numbers for which the formula makes sense. And that set in this case is the set of all non-zero complex numbers. Non-zero complex numbers have reciprocals. 0 does not have any reciprocal. So this is the largest possible domain of definition of this function. If you however want to restrict the domain, you want to have a smaller set somewhere in the complex plane, then you have to specify that explicitly. And we often refer to this function with this equation, w equals 1 over z, or sometimes even more simply like this, 1 divided by z. This is the common practice, where you show what the dependent variable is on one side, on the left hand side, and on the right hand side you have a formula involving the independent variable. So that's how a function is normally given in complex analysis. And along with such a formula, if you want to specify the domain, then after the formula you write comma and then you write what the domain is, which usually comes in the form of some inequalities, something. Example 2, here we consider the square function. We are taking a complex number and squaring it. The square is the output. And in this case, obviously, the largest possible domain of definition is the entire set of complex numbers, because every complex number has a square. Now say we write the input z as x plus iy, and then with that, let's calculate f of z. If you go through the calculation, which is a simple thing, this is what you find. After expanding this square and expressing the result in the standard form, so you find that that function u of x comma y in this case is x squared minus y squared, whereas v of x comma y is 2xy. This is the real part of the square function and this is the imaginary part of the square function, and both of them are real valued functions of two real variables x and y. Now instead of Cartesian coordinates, if one uses polar coordinates to express the input, The input of course has to be non-zero. Note that in this case you can take z equal to 0. For that specific value there is no polar representation, but for other values there are polar representations, and if one uses that, then let's see what it becomes. So you now have to take the square of r times e to the power I theta. From properties of this type of numbers, that becomes just this. You take the square of r, and here also you multiply theta by 2. We already saw before why these things happen. You remember de Moivre's law, that thing. So then you write what this thing is. Cosine of 2 theta plus I times sine of 2 theta. Multiply that by r square and you get this. R square cos 2 theta plus I times r square sine 2 theta. So u of r comma theta is this and v of r comma theta is this. Example 3, where the function is this. We take the square of the absolute value of the input. Note carefully that this is a real number. It is a complex number, fine, but actually it's a real number. For this function also, like the square function, the largest possible domain of definition is the entire set of complex numbers. Okay, I did not write that thing again. Now, if you express the input in this Cartesian form, standard form, then you know what the output is, x squared plus y squared. So you see that this is a real valued function. So that is why such functions are sometimes called real valued functions of complex variable. Note that in this case the function u is x squared plus y squared, u of x comma y is this, and there is a v. It's not that v is not there, v is there, but v is the constant function 0. V of x comma y equals 0 for all x and y. Next we consider a class of functions, class of complex valued functions instead of a single example. Let n be a non-negative integer. That means n is either 0 or positive. And let these be complex numbers, a0, a1 up to an. Then you consider this function p of z, which is a0 plus a1z plus a2z squared. That's the pattern. You already know what these things are. And finally you have an z to the power n. We call this function p a polynomial of degree n if the coefficient an is not equal to 0. Actually, I should have written this condition here itself. I forgot. But anyway, so this is a polynomial or a polynomial function, complex function which is in the form of a polynomial of degree n if this coefficient is non-zero. So you see that in this case we are not looking at a single example, but rather at a class of functions which has many functions, infinitely many in fact. That is because you can change this n and you can also change these coefficients. So that's how we get the class of polynomial complex functions. In this class, every function has the entire set of complex numbers as its largest possible domain of definition, which is obvious because for any complex number set, this formula makes sense. It gives you another complex number. Next, let us consider quotients of polynomials, that is, functions which look like this, p of z divided by q of z, where p and q are both polynomial functions. Then such functions are called rational functions. This is also a class of functions instead of a single function, because you can change these polynomial functions. Just like the class of polynomial functions has infinitely many functions, the class of rational functions also has infinitely many functions. Note one more thing, that the class of polynomial functions is contained in the class of rational functions, because you can choose this denominator to be the constant polynomial 1. Then this rational function just becomes the polynomial function p of z. That is why the largest possible domain of definition of this rational function is, of course, the set of all complex numbers where the denominator polynomial does not vanish. Recall that in our example 1, the reciprocal function is a rational function like this, where the numerator is the constant polynomial 1 and the denominator is the polynomial z. You also go back and see what the largest domain of definition for that function is and match that with this one. You will see that they are the same. Sometimes in complex analysis, we have to consider functions which are not functions in the traditional sense. That's because for each input, they do not give a unique output, but rather more than one output. So what we do in such situations is we choose one output for each input in some systematic manner. We create an ordinary function and then we study that function. In fact, we have already come across an example when we considered roots of complex numbers. For a positive integer n, a given complex number has n different roots, nth roots. So there itself you have multiple values for a given non-zero complex number, of course. So let's see one example like that. Example 4 says z is a non-zero complex number. Now we already know from that section where we considered roots of a complex number that z has two square roots, which are these: plus or minus square root of r times exponent of I times theta divided by 2, where r is the absolute value, that is modulus of z, and this theta is the principal value of arc z, that means capital arc z. Now from those two values, if you systematically choose only the positive square root of r, then you get this function. F of z equals square root of r times exponent of I times theta divided by 2, where r is positive and theta being the principal argument satisfies these inequalities. Note that for this function, the largest possible domain of definition is the set of all non-zero complex numbers. But because 0 is the only square root of 0, I mean the complex number 0, so you can also include 0 in the domain by defining a slightly larger function. Larger function means having that extra input 0 where the output is also 0. So that way you get a square root function which is an ordinary function, not a multiple valued function.